Hey everybody, it's Mr. N, and we are going to do our next lesson here, which is on exponential functions and their derivatives. So let's start with reminding ourselves what an exponential function is. That's f of x equals a to the x. So if a equals positive, then a to the x equals the limit as r approaches x of a to the r, where r is rational. Basically, it means that if you've got something like this, let's say 3.14, 5 to the 3.14, 5 to the 3, 5 to, see what's happening? It's going on. This becomes the limit, which is 5 to the pi. So now if we take a look at this, and we are graphing f of x for equals a to the x for different values of a, what you'll notice is as a gets to be larger, then it will hug the axes a little bit more. So this is larger a, and then this is smaller a. And I'm saying a being smaller a, meaning a is greater than 1. Now, if a is in between 0 and 1, such as like 1/2, then it'll look like that. Okay, but they'll all cross through that same point right there that they all have in common, which is 0, 1. All right, and Stuart does a good job of showing that in the book over there. So let's move on over here. So we have this theorem now. If a is greater than 0 and a doesn't equal 1, then f of x equals a to the x is a continuous function with domain all reals and range from 0 to infinity. In particular, a to the x is greater than 0 for all x. If a is between 0 and 1, then a to the x is decreasing. So those are the graphs that we're talking about. If a is greater than 1, f is an increasing function. If a, b greater than 0 and x, y, z in reals, then we have these situations. So these are the laws of exponents that you guys have already been taught. If you have the bases that are the same and you're multiplying, then you can add the powers. If you have the power here, this should say a minus, that's a typo. This should say a minus. That should be minus xy. Okay, so this is a to the x minus y. Then we're dividing it. It goes similar to this, where if we're multiplying like that. Okay, then next over here, if you have a to the x and you're raising it to a power, then we multiply the powers. All this is kind of confusing, but hopefully your algebra teachers did a good job of explaining these to you, because it's like we multiply, but then we add. We raise to the power, but then we multiply. So it's kind of like a little confusing, but hopefully they did a good job of explaining this to you. Over here, ab to the x, well, the x is just distributable. So then we have these situations where if a is greater than 1, then we can say the limit as x goes to infinity, a to the x is equal to infinity. Look at the graph, and it'll make sense. Same thing here. As x goes to negative infinity, a to the x goes to 0. So that's this part of it. Over here, as x goes to infinity, a to the x, this is between 0 and 1. Now we're looking at the blue one. Then a to the x equals 0. And the limit as x goes to negative infinity, a to the x, well, that's going to be the blue graph again, where we're going to go to infinity. So now here, those are just a review of all the ones you've been taught, but now here's the new stuff. Okay, how do we take the derivative of an exponential? Well, if we have the derivative of a to the x, this becomes a to the x ln a. The question might be why, but we'll discuss this later when we get into the nitty-gritties of this. But right now, this is the one I want you to memorize off the bat. The derivative of a to the x, which is your power function here, is a to the x, your exponential, sorry, is a to the x ln a. So then we have got the number e. And this is Euler's number. Some say Euler, some say Euler. Now, if we had this compound interest formula, which you probably learned in your second algebra course, so algebra 2, a equals p to the 1 plus r over n to the nt. This is compound interest. If I take my number of compounds and increase this to be an infinite amount, okay, so ignore the r, ignore the t, because those are constants that I can work with. But if this n keeps changing, and I'm going to make this infinite, so I'm going to take n as it goes to infinity, I'll take that limit, I get this value, which is e. Different ways to define e. That's just one way. The book defines it as a limit as h goes to 0 of e to the h minus 1 over h equals 1. Many calculus books would do it this way instead. But that's the basics of how we get e from algebra. We take this limit, and we end up with this value. So visually, let's take a look at this. I'm going to slide this up just a little bit here. And this is telling me that if I were to graph this, and I get something that looks like this, and I'm graphing this equation right here, the limit as h approaches 0 right there, okay, this would be the slope, which is 1. So if f of x equals e to the x, then the slope of the tangent at, or I should say 2 e to the x at 0 equals 1. Okay, that's visually what it's telling us. And then we've got another definition. This one says that a positive real number such that the ln of e equals the natural log of e equals the integral from 1 to e of 1 over t dt, which is equal to 1. So basically, ln of e is 1, and that's something that you guys have already been taught. So here's the derivative of e. Since we talked about the derivative of a to the x, here's the derivative of e. The derivative of e to the x is just e to the x. But we always need to apply a chain rule. So derivative of e to the u will be e to the u du dx. That's the chain rule part of it. So let's do a couple of these. On this first one, we're going to say that dy dx, they want us to find dy dx, that's just, since it's e, it's just going to be e to the 1 over x squared. But now I have to apply the chain rule part. So on this part, we have x to the negative 2, right? So this will be negative 2 times x to the negative 3. Now, cleaning all this up, I will get negative 2 e to the 1/2, or 1 over x squared, sorry, and x to the 3rd on the bottom. Okay, let's take a look at this second one. On the second one, we've got this situation, so dy dx is just going to be e to the negative 3x squared times, now I need to chain rule that, that's going to be negative 6x to the 1st. And rewriting all this, I'm going to get negative 6x e to the negative 3x squared. All right, so moving on, over here, the properties of f of x equals e to the x, which is our natural exponential function. The first property is f of x equals e to the x is increasing continuous function with its domain, all reals, and range from 0 to infinity. Second property, e to the x is going to be greater than 0 for all x. You can graph it and tell. And the graph, the x-axis is a horizontal asymptote. So if you graph this, it'll show everything I'm talking about here. And I will sketch a quick graph of it for you guys right here. And this is what it looks like, right? And right there it goes through the point 0, 1, because anything to the 0 is going to be 1. And that's what it looks like. So you can see that the domain is all reals, the range is that, e to the x is greater than 0 for all x, it's always going to be above the axes, and the graph, the x-axis right here, is our horizontal asymptote. And now we have the limit as x approaches negative infinity is going to be 0, and the limit as x approaches negative, this should say positive infinity right there, that should say positive, another typo, I've got a few typos here, and that will be infinity as well. All right, what about when we integrate e to the x? Well, guess what? If the derivative of e to the x is e to the x, then the integral of e to the x is just going to be e to the x plus c. But of course, some problems may involve a substitution rule. All right, let's do a few examples and see how this works out. On the first one, we want to integrate e to the 3x plus 1. So I will do this by substitution for you guys, and I'll say let u equal to 3x plus 1. So that means du equals 3 dx. And I'll substitute that in, so I'll get the integral of e to the u, and then this dx is going to be du over 3. So du over 3. So this is 1/3 times the integral of e to the u du. And e to the u, the integral is just e to the u. So 1/3 e to the u plus c. And I make my resubstitution 1/3 3x plus 1 plus c, just like that. All right, moving on to our second one over here. And This time I'll let u equal the negative x squared. So that means du is going to be negative 2x dx. So if I solve for the dx, du over negative 2x is my dx. So this substitution becomes 5x e to the u du over negative 2x. Well, the 2x, the x's go away, so then I end up with 5 over negative 2 integral of e to the u du. So this becomes 5 over negative 2 e to the u plus e to the u plus my c. So negative 5 halves e to the negative x squared plus c. Our next one, let's take a look at what we got. Let's take a look at what we can do. And over here, I'm going to let u equal this 1 over x, this part right there. So du equals, over here, this is going to be negative 1 over x squared dx. So I end up with negative x squared du equals dx. So I have the integral from e to the u over x squared, and this is negative x squared du. So that goes away with that. I put the negative out in front, and I'll integrate, and I'll just get negative e to the u plus c. So this becomes negative e, and u is negative 1 over x squared plus my c. Oops, e is 1 over x. Sorry, just 1 over x. Let me erase this, see if I can write it out a little bit better. The u is 1 over x. Okay, there we go. All right, let's take a look at the next one. Find the area bounded by these regions. So over here, that means I need the integral from 0 to 1 of e to the negative x dx, right? That's what I'm looking for in this one if I want the area bounded by that, because e to the negative x will look like this, and I'm going from 0 to 1, so that's this area right there. And over here, I'll end up with, this ends up being, if you do the substitution part, or you could just do a guess and check at this point, negative e to the negative x on the bounds from 0 to 1. So this becomes negative e to the negative 1 minus negative e to the 0. And that comes out to be approximately 0.6321. Because over here, e to the 0 just comes out to be 1. Okay, moving on. On this next one, when I put this together, let's see what we got. E to the x cosine x. Well, again, I'm integrating this from negative 1 to 0, and this is going to be bounded by this curve, and this will kind of bind itself if you graph it. So you'll end up with e to the x cosine e to the x dx. So real quick to show you, this graph is kind of funky, but I'm only looking at the negative 1 to 0 part, which ends up on this part kind of coming up like this. So that's the area you're finding right there. Okay, so let's see how we can go ahead and integrate this. You could just let u equal e to the x and make that substitution, but if you just see this and kind of guess and check at it, you'll realize that this is sine e to the x, right? Because if I take this derivative, I'll get cosine e to the x, chain rule e to the x times 1. So I'll get that whole situation right there, and that'll be from negative 1 to 0. Again, if you wanted to do this, just let u equal e to the x and work on it that way, and you can make your substitutions. But I think you'll end up with pretty much the same thing. You'll end up with u cosine u, which pretty much is the same. Okay, so over here, plugging this in, I'll get sine e to the 0 minus sine e to the negative 1, and I'm just going to do this as a decimal. That comes out to be 0.482. All right, we'll leave it at that. So hopefully that wasn't too bad. We're going to do more examples in class. Thanks for watching. Hit that like and subscribe button, and I'll see you guys in the next video.